All right, let's switch our gears, talk about Heaps' law. So suppose you do the following experiment. You take a book or a newspaper or a website, whatever you want, and you start reading it. And every time you see a new word, a word that you haven't seen in this book before, you're going to record it. You're going to keep a counter of the number of new words that you have seen. So let's say that this counter is V, the number of new words that I've seen, and N is the total number of words that you've read up until this point in a book. Now, let's take V and plot it as a function of N. So if you do it for just about any domain, you will have a picture that looks kind of like the picture on the right. I have N, the total number of words on the x-axis. I have V, the number of new words or distinct words on the y-axis, and the graph there is a function of V over N. And in general, for many, many domains, it will look kind of like the square root. So the number of new words or distinct words, it grows quickly at first and then it starts slowing down, which is kind of natural. In the beginning you see a lot of new words and then you stop seeing, you see more and more of repeating words. Right. So this is known as Heaps' law, and the general formula from that is that. So you take N, the total number of words that you've seen up until this point, you raise it to some power B, multiplied by some constant K, and you get the number of distinct words that you're going to see. Now, K and B, again, are parameters. So K is typically in the range between 1 and 100, and B, or beta as I have it there, is usually a number around 0.5. And where do you get these parameters? Well, you have to fit them. Different corpora will have different K and B parameters. So you look at this and you say, well, this is probably just because I'm doing it over a relatively small data set, right? So the figure that I have, this is AP89, so it's a small data set. If I did it for a larger data set, it should tail off eventually, right? Because you will stop seeing new words at some point. There's only so many words in the English vocabulary. But that turns out not to be the case, right? So here I'm showing a graph of Heaps' law for a much larger data set. So this is Gov2, and on the x-axis I have about 25, 30 million. On the x-axis I have about 25 billion terms, so it's a large collection. And what you see is that the number of distinct words keeps growing. It never stops, it never tails off. Right? So what's happening there? We got to 30 million distinct words and it's still growing at a very brisk pace. So why is this happening? The reason this is happening, these are the words that you keep seeing are not words in your normal English dictionary, right? So, because the dictionary is finite and it's much smaller than 30 million. So what are these? These are things like spelling errors, right? People will misspell words in lots of different and creative ways, but that's not it. That's not the only thing that happens. You also have product names. Right? People like to create new names for the products. You have personal names, company names, emails, bits of code. So what's happening there is you are seeing the human tendency to invent new words for the things that they want to name. People like to name things, and that's what's happening even in news data sets. So it's accurate for many different collections. It happens all over the place. Now for different domains, you will have the different values of K and B, but Zipf's law overall is is a law that holds for just about any collection of text. And by the way, this is not specific to English. It holds for other languages just as well as English. Now, so it's you can usually find a pretty good fit. K and B together give plenty of flexibility to fit the data. Sometimes the fit is poor for either the small n or the large n, but in general you can get a fairly good fit.